Imagine a world vastly different from our everyday experiences, where energy comes in discrete packets and particles behave like waves. This is the captivating realm of quantum mechanics. Unlike classical physics, it delves into the strange world of the very small. Quantum mechanics has shaped the modern world in countless ways. For centuries, scientists debated the nature of light. Was it a wave, like ripples on a pond, or a stream of particles, like tiny bullets? The answer, as revealed by quantum mechanics, is both. Light can exhibit properties of both waves and particles, a concept known as wave-particle duality. In the 17th century, Isaac Newton proposed the corpuscular theory of light, suggesting that light was made up of tiny particles called corpuscles. This theory explained reflection and refraction, but struggled to account for other phenomena like diffraction and interference. In the 19th century, experiments by Thomas Young and others provided strong evidence for the wave nature of light. Young's double-slit experiment demonstrated that light passing through two closely spaced slits creates an interference pattern, a hallmark of wave behavior. However, the early 20th century brought about a revolution in our understanding of light. Albert Einstein, in his explanation of the photoelectric effect, proposed that light also behaves like a stream of particles called photons. The photoelectric effect, where electrons are emitted from a material when light shines on it, could only be explained if light carried energy in discrete packets or quanta. One of the most profound consequences of quantum mechanics is the quantization of energy. In the quantum world, atoms and other systems can only possess specific discrete amounts of energy, known as energy levels. This is in stark contrast to classical physics, where energy is continuous and can take on any value. When an atom absorbs energy, an electron can jump from a lower energy level to a higher one. Conversely, when an electron falls from a higher energy level to a lower one, it emits energy in the form of a photon. These transitions between energy levels are known as quantum jumps or quantum leaps. The energy of the emitted or absorbed photon is directly proportional to the difference in energy between the two levels. This relationship is described by Planck's equation E equals hf, where E is the energy of the photon, h is Planck's constant, and f is the frequency of the light. The quantization of energy has profound implications for our understanding of the universe. It explains why atoms are stable, why they emit and absorb light at specific wavelengths, and forms the basis for many modern technologies, including lasers and spectroscopy. The concept of wave-particle duality, where particles like electrons and photons can exhibit both wave-like and particle-like behavior, is one of the most counterintuitive and perplexing aspects of quantum mechanics. It challenges our classical intuition, where objects are neatly categorized as either particles or waves. How can something be both a wave, spread out over space, and a particle, localized at a specific point? The answer lies in the probabilistic nature of quantum mechanics. In the quantum world, we can only predict the probability of finding a particle at a particular location. When we perform an experiment to measure the position of a particle, we force it to choose a definite location, collapsing its wave function. However, before the measurement, the particle exists in a superposition of states, meaning it is in all possible positions at once, weighted by their respective probabilities. The wave-like nature of particles is evident in phenomena like electron diffraction, where electrons passing through a narrow slit create an interference pattern, just like waves. This behavior is impossible to explain if electrons are treated as classical particles. Section 5. Heisenberg's uncertainty principle. One of the most profound and, unsettling principles of quantum mechanics is Heisenberg's uncertainty principle. This principle, formulated by Werner Heisenberg in 1927, states that there are fundamental limits to the precision with which certain pairs of physical properties can be known simultaneously. The most famous example of the uncertainty principle is the relationship between a particle's position and momentum. The more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. This is not due to any limitations in our measuring instruments, but rather a fundamental property of the quantum world. Mathematically, the uncertainty principle is expressed as dx dp is greater than or equal to h divided by 4pi, where dx is the uncertainty in position, dp is the uncertainty in momentum, and h is Planck's constant. This equation tells us that the product of the uncertainties in position and momentum must always be greater than or equal to a certain minimum value. The uncertainty principle has profound implications for our understanding of the universe. It means that at the quantum level, there is an inherent fuzziness or indeterminacy in the behavior of particles. We cannot know both the position and momentum of a particle with arbitrary precision. Section 6. Quantum tunneling. Escaping the confines of classical physics. Imagine a ball rolling up a hill. In classical physics, if the ball doesn't have enough energy to reach the top, it will always roll back down. However, in the quantum world, there's a chance that the ball could tunnel through the hill and appear on the other side, even if it doesn't have enough energy to overcome the barrier. This seemingly impossible feat is known as quantum tunneling. Quantum tunneling is a consequence of the wave-like nature of particles. In quantum mechanics, particles are described by wave functions, which represent the probability of finding a particle at a particular location. When a particle encounters a potential barrier, its wave function doesn't simply stop at the barrier but rather extends into and even through it. The probability of tunneling decreases exponentially with the width and height of the barrier. However, for very thin barriers, the probability can be significant, allowing particles to tunnel through barriers that would be insurmountable in classical physics. Quantum tunneling plays a crucial role in many physical phenomena, including nuclear fusion in stars, the operation of transistors, and scanning tunneling microscopy. Section 7. Quantum entanglement. Spooky action at a distance. One of the most bizarre and counterintuitive predictions of quantum mechanics is quantum entanglement, a phenomenon where two or more particles become linked in such a way that they share the same fate, even when separated by vast distances. Imagine two entangled particles, each in a superposition of states, say spin up and spin down. When we measure the spin of one particle, we instantly know the spin of the other particle no matter how far apart they are. This instantaneous correlation between entangled particles has been experimentally confirmed and violates our classical intuition about locality and the speed of light. Einstein famously referred to entanglement as spooky action at a distance because it seemed to imply that information could travel faster than light. However, quantum entanglement does not allow for the transmission of information faster than light. While the implications of entanglement are still being explored, it has the potential to revolutionize fields like quantum computing and communication. Section 8. Applications of quantum mechanics. Quantum mechanics, despite its mind-boggling concepts, is not just a theoretical curiosity confined to the realm of physics laboratories. It has led to a plethora of technological advancements that have revolutionized our world and continue to shape our future. One of the most well-known applications of quantum mechanics is the laser. Lasers, which rely on the principle of stimulated emission, produce highly focused and coherent beams of light used in telecommunications, barcode scanners, laser surgery, and countless other applications. Another groundbreaking invention rooted in quantum mechanics is the transistor, the building block of modern electronics. Transistors, which control the flow of electricity in circuits, are found in virtually every electronic device, from smartphones and computers to televisions and medical equipment. Quantum mechanics also plays a crucial role in medical imaging techniques like magnetic resonance imaging, or MRI. MRI uses strong magnetic fields and radio waves to create detailed images of the inside of the body, allowing doctors to diagnose a wide range of conditions. Other notable applications of quantum mechanics include nuclear energy, electron microscopes, and global positioning systems, or GPS. Section 9. The future of quantum exploration. The exploration of the quantum world is far from over. Scientists are still grappling with the profound implications of quantum mechanics and its potential to unlock new technological frontiers. One of the most exciting areas of research is quantum computing. Quantum computers, which harness the principles of superposition and entanglement, have the potential to solve certain types of problems exponentially faster than classical computers, revolutionizing fields like medicine, materials science, and artificial intelligence. Another promising avenue of exploration is quantum communication, which aims to exploit the principles of quantum mechanics to create ultra-secure communication channels. Quantum cryptography, for instance, promises to enable the transmission of information that is fundamentally impossible to eavesdrop on. As we delve deeper into the quantum realm, we can expect even more mind-boggling discoveries and technological breakthroughs that will continue to shape our understanding of the universe and transform our world in unimaginable